name is Lily Alterman, and today I'll be presenting to you Lab 3 circuits. Now, what was the purpose of lab? The purpose of the lab was to predict the behavior of the circuit containing resistors in series. It was also to use multimeters to measure the actual values of conventional current and the potential differences in the circuit, and it was also to examine the behaviors of the ohm resistors and capacitors in a circuit. Now, a little overview of the results of this lab. The current in the first circuit was 0.02 amps, and we found this by measuring and by also calculating where the loop and node rules did apply. And as the resistance increases in the RC circuit, the charge and discharge rate of the capacitor increase, and the charge time constant for the second RC circuit for the 15 ohm light was 1 minute and 12 seconds, and for the 3 ohm it was just 13 seconds. Now, as a little introduction, first off, we have Kirchhoff's loop law. This is the round-trip potential difference for static electric fields is zero because of path independence. So this basically says all the voltages added up in the circuit should all equal zero. And then Kirchhoff's node rule is for a certain steady state, the current entering the node must equal the current leaving the node, which basically means the current in has to equal the current out. Then Ohm's law, which is a relationship between voltage, resistance, and current, is depicted by this formula right here. This is the voltage equals I times R, and we can also rearrange this formula to solve for different parts of the equation. Like for I, it would be V divided by R, or for R, it would be V divided by I. And then also right here, this is just a little overview of the resistor color code. I use this to make sure we were using the right resistors in the lab, and it's a very easy thing to remember. It's just black, brown, and then the rainbow, gray, white, and then gold and silver if needed, and then 0 through 9 just go through that and represent the numbers related to the colors, and then the gold and silver are used for our tolerances and multipliers if needed. Now, we also have resistors in series and resistors in parallel. When resistors are in series, the current flows through each resistor and is the same since there's only one path for the current to flow. It is represented by this formula right down here. We just sum up all the resistances. And as you can see in this little picture, this demonstrates how a resistors in series would look. And then resistors in parallel is when the resistors are in parallel, the voltage across each resistor is the same, and the equation is the reciprocal of all the total resistance equals the summation of the reciprocal of the resistances themselves, as represented by this equation down here. And then you can see this picture right here depicts how a resistors in parallel look. Now, experiment. The circuit one initial conditions. The system is the circuit and all the components attached. The surroundings was everything on the table and everything that possibly could come in contact with the circuit and its components. The circuit one is right here. It consisted of two batteries, 1.4 volts, 1.5 volts each, 3 volts total. It had 2 amp meters used, and then these resistances and these resistors. The predicted currents for I1 and I2 were both 0.02 amps, and the assumptions I made while doing this was that all equipment and measuring tools functioned as anticipated and properly, and the wires and other components were not adding extra resistances to the circuit that were not expected to. Now for circuit 2, this was the RC 1 resistor and 1 capacitor circuit. The system and surroundings and assumptions all remained the same. The only thing that's different is that this circuit then got changed to actually solve and experiment what we wanted in the lab. But the original circuit was 1 farad capacitor and just 1 resistor, and the battery source, which is the same from the previous circuit, would just be hooked up when we wanted to charge the capacitor. Next, we did have to transform this circuit, so we did have to design our own a little bit. Here is the entrance of where we would have our batteries right there. This would be able to, was removed from the circuit when we wanted to measure the charge and discharge rates of the capacitor accordingly, and we still had our 1 farad capacitor right here, and the only real addition was we put a 3 ohm or 15 ohm LED, not LED, incandescent bulb on it to visually see these discharge and charge rates. Now, these are the visual circuit constructions. This is just them made with our alligator clips and are the same as the schematics shown in the slides below. Now, the circuit one experiment questions. For number 2, I1 ended up being 18.9 milliamps, I2 and then I2 ended up being 18.9 milliamps too. And when you reverse the connections, the values were the same as above, just negative. And if we convert one of the ammeters to a voltmeter by changing the mode on the multimeter, the new voltmeter would read positive 3 volts and the ammeter would read 0 amps. And this is because the multimeter acts as a high resistance to measure voltage, thus the current, which is V divided by R, is unable to travel through and the ammeter reads 0 amps. And right here, these are all the different potential differences across the circuit elements. It was negative 0.04 volts across this wire, negative 0.093, and a negative 0.195 volts across this section right here for our resistances, and another negative 0.005 volts, and another negative 0.01 volts right here, and then our battery was a collective of positive 3 volts for our circuit. And when we sum that up, we end up getting a positive 0.03 volts. Theoretically, this should be 0 volts because of Kirchhoff's loop law, and this is because the error could come from the resistance in the ammeter or errors just in the testing equipment that got us a little bit off. But based on the tolerances in our system, I would say this is still a pretty good answer. And this was just the approximate graph of the potential across my circuit and how it ended up being. It never completely got to 0, but it was very close to it and very closely approaching. Now, when you attach a voltmeter, you alter the circuit. Why doesn't the resistors ammeter resistance change? The voltmeter has a high resistance and the ammeter has a low resistance, so the voltmeter pulls little current from the circuit, thus the ammeter's resistance does not change. And then you connect the voltmeter across the 100 ohm resistor, and the ammeter reading just does not change. Now, if you replace the voltmeter in parallel with the 100 ohm resistor, the reading is now 46.5 milliamps as the ammeter has low resistance. And based on the measurements I got before, I calculated it using V divided by I to find R. And here were the values just right here. They all are within tolerances for the resistors based on their color code and are accepted values, and the same for the wires and ammeters themselves. Now for circuit 2, this was once again the one we originally had with our LED and our capacitor. We had 2 light bulbs, a 3 ohm, which was a low resistance one, and a 15 ohm, which is a high resistance one. As you can see right here, we have a little video. This was a time lapse of the capacitor charging and discharging, and thus what it showed on the LED. And the charge and discharge times can be seen below. For the high resistance, the charge time was 1 minute 12 seconds. Discharge time was 1 minute 2 seconds. For the low bulb, the charge time was 13 seconds, and the discharge time was 11 seconds. Now for the RC time constant. The RC time constant is calculated by R times C, which does equal tau, or a time constant. For the low resistance bulb, that ended up being 3 seconds, and for the high resistance bulb, that ended up being 15 seconds. Now 5 tau, or 5 R times C, is equal to the predicted time it should take for the capacitor to fully charge, and when I calculated this out and compared it to the measured time, it was very close and within a reasonable tolerance, so I can say confidently that these capacitors probably charged completely. Now the results, the values gained were identical or within a degree of reason to the predicted values, and the small differences can be accounted for based on device specifications or tolerance, intolerances, or minimal errors listed below, which the possible errors were human handling, equipment poorly, equipment errors themselves, and errors in calculations by not taking into account things like the resistance of the wire or the resistance of the ammeter. Now the what if you charged a capacitor with no resistor in the circuit? And how would this work with an ideal model, and how would this work within our actual model? So if you charge the capacitor with no resistance in the circuit, the ideal model would take 0 tau or 0 seconds to charge because the RC time constant tau equals R times C, and if R equals 0, then the time constant should be 0. When we performed this in real life, the charge took about 7 seconds. We tested with a high resistance light bulb. These measurements differ due to the small amounts of resistances in all the components, such as the battery, ammeter, and the light bulb itself, and these slow down the time, making it not perfectly 0 seconds. Now, here are my citations. Thank you so much and have a lovely day.